So Sam asked me this interesting question about the geometric significance of things, and we're actually going to be looking at the geometric significance of these equations that we've been looking at. And at the moment, we've had them in quite like abstract things about like the number of sheep, the number of mole rats, the number of visitors to theme parks, all of that kind of stuff. And we're going to instead be trying to think about what do these equations look like. Now you're going to bear with me for a bit. We're going to talk about what equations look like in 2 dimensions when we just have x and y. Because if we can understand what it looks like with x and y, the jump that we then do to go into the 3rd dimension is going to be slightly easier for us to do. So consistency of linear equations. Consistency is basically a word that just means do the lines intersect? Are the equations consistent? And it says from pure year 1, you were already familiar with the idea that the solution of a system of 2 equations with 2 unknowns can be visualized by finding the point of intersection of 2 lines. A system of linear equations is known as consistent if there is at least one set of values that satisfies all the equations simultaneously, i.e. it has at least one point of intersection. So when I say is something consistent, it just means does the system of equations have some possible values that can make all of them true at the same time? Does it consistently bring truth to all of the equations that we have in that system? So we could have a system of equations that looks like this: x plus 2y equals 1 and 3x minus y equals 0. This, if I was to visualize it, would be 2 lines that do intersect each other. So there is a consistent, this system of equations is consistent and it has got a solution. And if I was going to put that as a matrix, we can see it would be 1, 2, and 3 minus 1. That matrix is non-singular. What does that mean that it is non-singular? The determinant does not equal 0. Remember, singular means it doesn't have an inverse, so we think it's singular. It's a matrix that is by itself. So this one has a non-singular matrix. It has an inverse. It obviously has to have an inverse because that's how we would solve this equation, wouldn't we? We would use the determinant and the inverse to be able to find that. What's the other thing it could be, a system of equations, is it could be 2 lines that are parallel and that they do not intersect each other. So I've got x minus 3y equals 1 and x minus 3y equals 2. This system of equations is inconsistent. It has no solutions. And the thing that's obvious to see that these are inconsistent is x take away 3y being equaling 1 and x take away 3y being equal to 2. That's obviously inconsistent. There obviously can't be both true at the same time. How could it be equal to 1 and equal to 2 at the same time? It just is what we call something that is inconsistent. And we should notice about this matrix that its determinant is 0, which makes sense because there's not going to be an inverse for it, which means we can't find a solution to this simultaneous equation. The last one that we have is, now this is very difficult for me to have represented, but actually this system of linear equations are, when you look at them, what can you see when you look at them? It's doubled. So actually, they're representing the same line. This representation I have here is trying to say that those 2 lines are actually the same line. Yeah, it's basically just one line. I just did it as 2 so that you can see that so you can actually see that there are 2 lines that are there. Now this is consistent because whatever I pick for x here, I don't know, maybe I say that x is 7 and y is 2. Well, if x was 7 here and y was 2 here, it would also work. I could pick a different value for x and a different value for y, and this one would work. So there's a lot of solutions to this particular equation. So it is consistent because the 2 equations together are speaking the same truth. They're still saying that. Pardon?
Write the matrix 1 minus 3, 1 minus 3.
Oh, sorry, this is not correct. This should say 1 minus 3 and 2 minus 6. Let me just change that. This should say 1 minus 3 and 2 minus 6. Well spotted. And it has infinitely many solutions. Because you can imagine that could be a solution. This value, this x and y value, this x and y value, this x and y value, any of those things could be a solution. This one over here, that's the only place that there is a solution. This one has no solutions at all. And now we're going to extend we're going to extend this idea into 3 dimensions. This is an area that people find sometimes confusing, so I want you to just like take in all the information, and then I've got a summary slide that I think should pull all of the ideas together. Are there any questions about these 3 situations? Because we're going to now extend this into 3 dimensions. Sam?
Is that matrix still singular?
Yeah.
Um,
I just tried it.
Yeah,
Just
tried
tried
it
my
first.
error.
Yeah, that is still singular. The only one that will be non-singular is when there is a one solution. Okay, this one, yeah, because we get -6 minus -6, you get 0. Yeah. Okay, so we're going to now think about what happens in 3 dimensions. Now, there's a lot of information on this page, and we're going to try and break down what's happening here. Now, I've said in chapter 9, which we haven't quite got to yet because it's very hard to put these things in a sensible order, you will learn that just as ax plus by is equal to c gives the equation of a straight line, when you add in this extra one for z, when you add in a 3rd variable, what you actually get is the equation of a plane. I think we mentioned that at the end of Monday's lesson. Again, we get solutions to the system of linear equations when all of the planes intersect. So previously, we were talking about where 2 lines intersect each other. We're now going to be talking about if all 3 planes intersect each other. So like the question you were just doing about the theme park, the solution or the coordinates of where all 3 planes intersected were the number of visitors to each of those theme parks, okay? So the best scenario, the easiest scenario to come up with, and this is the only one that we've dealt with so far in all of those questions you've done with the sheep and the bank accounts and the bats, is that all of the planes have one single solution. Although I've made these planes here like little rectangles, they're actually infinitely huge rectangles. Like this blue rectangle here is actually just going to be flat and covers the whole board and goes even bigger than that. But I have to be able to make them small enough so you can just see a little snapshot of what the planes are, okay? This is the first scenario that we've got. The system of equations is consistent. Why would we say that it's consistent?
One solution.
Because there's one solution, because there is a solution. Each of the equations will consistently be able to be true, and it has one solution. So we could actually say, when we get to this later, the matrix will be singular or non-singular? It'll be non-singular. It's like the first scenario we had with the lines, yeah? The second one that we've got here, we say that the planes form a sheaf. Now, the word sheaf is to do, it's like a bundle of things that you have together. And the way that these planes have intersected is they're kind of like a bundle of them. You sometimes use sheaf, you might hear it in like a farming kind of context where there's like a sheaf of like wheat. But it just is like a bundle of them together. And when you look at these planes here, they are intersecting in such a way that they're almost like the pages of like a book, like a double book kind of sandwiched together. And all of the planes are kind of intersecting, but they're not intersecting at a single point. They're actually intersecting with an entire line going through them. So anywhere, here, 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 any of those things would satisfy all 3 of the equations and would make all of them true consistently. So that would also be a consistent one. They have a line of intersection consisting of infinitely many points. The system of equations is consistent and has infinitely many solutions. This one is going to be singular. This one we said was non-singular.
So that one that we just got was like the 2 lines down, like each, or not each, like there are multiple.
Sort of. It's actually, there's going to be something that's different. This one is kind of like one that we haven't been able to deal with in 2 dimensions. It's sort of like that one, but you're going to see another one when you'll be like, oh, that's the one that's like that, okay? The scenario 3 is the planes form a prism. And when I'm talking about a prism, I'm talking about like this bit here. That's what I'm talking about, the prism that it looks like it's forming. So it looks like there are some solutions. It looks like the green one and the blue one have a solution along here. The green one and the orange one have solutions along here. The orange one and the blue one have solutions along here, but there is no place where all three of the planes have a solution at the same time. So I could say here, the green one and the blue one are consistent, but the orange one isn't. So the system of equations is inconsistent. Consistent is referring to whether they can all be true at the same time. There is nowhere that these can all be true at the same time. So it says, while the planes intersect in pairs, they don't all intersect at any point. The system of equations is inconsistent, and again, it is going to be singular. The last, well, not the last scenario, there's one more scenario on the next page as well. This says that two or more planes are parallel and non-identical. So here, we've got two of them that are parallel to each other. They obviously can't intersect. If they're parallel, they're not going to be able to intersect. How do you think you would be able to tell if two planes are parallel? What about if I say I had x plus 2y equals 3? What about if I had 2x plus 4y? What would it have to be equal to? If it was equal to 6, then it would be the same line. So anything other than 6, I don't know, let's just say 7. These two lines, if you were to make y the subject, you would find out that they would have the same gradient, but they would have a different y-intercept. So these would be parallel lines. So parallel planes will be the same. They will be multiples of each other, but they won't, this last part won't be a multiple, okay? And it says, again, this is inconsistent as the parallel planes never intersect, and thus all the equations can't be satisfied. And it says any rows in the corresponding matrix which are multiples of each other will be parallel. But we're only talking about the matrix side. We're only talking about this bit. If you look at these, if these are multiples of each other, then they're parallel. You just have to be careful that they don't actually, this last part isn't a multiple of it as well. The last scenario that we have, and again, this is singular. The last one that we have is that all the planes are the same. That's the one that's what you were saying, Ishraq. That's the one where they're all the same as each other. So these planes here are exactly the same as each other. The system of equations are consistent, and it's got an infinite number of solutions. This is a solution, this is a solution, this is a solution, this is a solution. Everything is a solution because they are all the same equation. And what this might look like as an example, it might be something like, oh, I didn't mean to draw that line, I can't be bothered to erase it. Like x plus 2y plus z equals 1. 2x plus 4y plus 2z equals 2. Minus x minus 2y minus z equals minus 1. These are all consistent because they're all the same as each other. They are all fully multiples of each other, okay? If I changed one of these numbers, so maybe I got rid of the minus, it would be inconsistent. What would it be representing, do you think? Two or more planes are parallel. It would be something where I've got a plane, another plane, and then something kind of cutting straight through them. So it would cross that one, and it crosses that one, but they don't all cross each other. These two, which are the parallel ones, are going to be those two, which are the parallel ones that we've got there. It's very, very abstract at this stage that we've got, okay? So I've made this extra slide so that you've got something that's like a reference for the whole thing. They are consistent, which means that there is at least one solution of all three equations. This means that all the planes are intersecting, and they can intersect in three kinds of ways, and I quite like the way that they can intersect. They can either intersect with something that has just got a single point. They can intersect as a line, or they can intersect on a plane. I quite like the fact that intersecting on a plane is a two-dimensional intersection. A line is one-dimensional, and a point has no dimensions. So there's like the three different ways that planes could intersect each other. The only thing that can happen if the matrix is non-singular is that they intersect at a single point. We say that the three planes intersect at a single point. This is the only one where the determinant is not 0. Everything else, the determinant is 0. Planes intersect along a line, infinitely many solutions. All equations are multiples of each other. They are the same equation. There are infinitely many solutions. Last bit here. They are inconsistent means that there is no solutions for all three equations at the same time, i.e. they are not all intersecting together. This could be a prism, which we've talked about. Again, it would be singular, or it could be parallel planes. The only one I hadn't shown you previously was this one that we had here. This one I had two planes being parallel and just some other one that was crossing them. This one, all three of them are parallel. So they're like stacked up, sort of books or three pieces of paper with a gap in between them. And it says that two or all rows of the matrix are multiples of each other, including the answer part. Oh, not including the answer part. Because if it was the answer part, it sends us up to this one that we've got up here. This is a really, every single time I've taught this, people find this really challenging. So if there's tiny questions, big questions, now is a really good time to just say, how does this work? Or can you just explain this thing again? How do you spot a prism? So that's a really good question. What we do if we think it's a prism, well, the first thing we would do is we would find out what the determinant is. If we find out what the determinant is, we know, let's say the determinant was 6, we know that the planes meet at a point. If it's not, we need to start checking some other things. If we then want to check if they are consistent. If they are consistent, we would then know whether it is on the top half or the bottom half. If they're consistent and they are not all exactly the same plane, then it's a sheaf. If they are not consistent and we don't have any of them that are parallel to each other, then it's a prism. And I guess the thing I need to show you about is how do we show if something is inconsistent? And I can do that on this next page because we're going to have a look at some of these equations that we've got here, and you're going to try and find out whether these things, what they actually represent. We're not going to have an awful lot of time to do this, so I might just try like a couple of them. You need to decide what each geometric it represents. It says, first of all, check what the determinant of the matrix is. If it is not 0, then they meet at a point. That's the nice one. That's just the easy one. The thing I'd probably suggest you do next is to solve the equation on your calculator to decide if it has one solution, meeting at a point, infinite solutions, which means it could be the sheaf or the same plane, or no solutions, which means it could be parallel planes or a prism. Because you know when you go to the simultaneous equation solver that you have, you can put them in just very quickly. And this is what I would recommend you doing in the exam, because the calculator will tell you whether they have got one solution, infinite solutions, or no solutions. The calculator tells you that. So you should start off informing yourself what the answer is, and then using maths to explain what your answer is. So why don't we just do this first one together? So we'll go to the equation solver, and we'll put it as simultaneous with 3 unknowns. Do you know how to use that?
Yeah.
And then you fill in your values.
Infinitely many solutions.
There are, oh, really? 3, 4, 1, oh, because I've typed it in wrong.
It should be the same thing because they're all multiple.
Good. So there are infinitely many solutions. When you type this first one in, you should see that there are infinitely many solutions. These actually represent the same plane because that one times it by 2, times it by 3. So this actually represents the exact same plane. And you would explain that by saying each of the equations is a multiple of the other one, so it's the same kind of plane that you have. And at least you've seen now on your calculator what it means when it says infinitely many solutions. If it has infinitely many solutions, is it consistent?
Yeah.
Yeah, it is consistent because all 3 equations can be true at the same time. But the matrix would be,
Singular.
it would be singular. It would be singular.
There's only one non-singular.
There's only one non-singular. So we've got about 10 minutes. I think this would be like a good thing for us to try and like finish off, and then we'll start next lesson going over some of these things as well. Okay? Yeah.
What does it mean after there's infinitely many solutions where it says like X equals 2
Yeah, that's really good. When it says on that one, it says x is equal to this particular thing, y equals y and z equals z. That means you can say whatever you want for z to be equal to. You can say whatever you want for y to be equal to. And then to find out what x is, you would do 2/3 minus 4/3 of what you've just picked for y minus 1/3 of what you've just picked for z. Okay? So that one, we also can tell that this is a plane because y and z are allowed to be whatever they like, which means that this must be 3 planes. If only one of them can be fixed, then you've got the sense of it maybe being a line. Okay, let's see if we can do a couple of these just to finish up what we've got there, okay?